Okay. Hello. Okay. If we're here for algorithms, okay. So I'm going to ask you guys to tell me how you feel about algorithms real quick, and the way you should feel about algorithms is really excited, and I'll show you what that looks like. Woo! Good. All right. So I'm Satish Rao, and I'm super excited, as you can see. And my co-teacher is co-instructor is, and I'm his co-instructor is Prasad Raghavendra.
Hey, I'm Prasad Raghavendra. I've been faculty at ECS for a few years. I've taught this several times, but it's the first time I'm teaching it with clearly excited Satish. I'm just as excited. Looking forward to teaching you all.
Okay, thanks. And did you want to say something? This is our 2/3 of our head TA team, and the other one, I don't know why he's up here, is Iman. If Iman's quite funny. He does imitations. He does an imitation of me that is fairly upsetting but pretty funny. So you can ask him for it if you want at some point. So.
Hi, I'm Dee. This is my 3rd semester teaching CS 170, and yeah, I'm really excited about algorithms too.
Hi, I'm Iman. This is my first time teaching CS 170, and I'm also excited about algorithms.
Hi, I'm Max. This is also my 3rd time teaching, and I'm not that excited about algorithms.
Max's blood runs cold. He's very calm. It's actually very nice to be around him. So, okay. So, yeah, okay. So let me just go quickly over the stuff, and then we'll get into some material. Okay, so over the staff and everything. So there's a static web page. The staff is here. I think I'll get this link to work someday, but it doesn't work right now. But this is the staff link. Okay, as you saw, this is Professor Raghavendra, who he looks quite young there, but he's a senior scientist at the Simons Institute of Theory of Computing. So he's really quite accomplished. I don't know who that guy is. That's some kid. But apparently it kind of looks like me. That's David. He's a head TA. He likes lifting. He's quite tall, so he has to lift it high. Dee likes penguins. Max likes to eat his corn in a row. You should ask him what he's talking about. I think it's this way. You eat the corn instead of this way. Iman, impressions, very funny. Julia, she's from Canada. Oh, Canada, oh, Canada. Neha is she likes cats. That's not very. Lots of people like cats, apparently. Ajay is a budding poet. Arpita is on the right. She likes dancing and tennis. Avni, she likes what was she? I'm trying to remember. Bioengineering. That's right. She's in bioengineering. Algorithms are everywhere. Carlo. He says y'all, which means I'm from Texas. Is that because he's from Texas, or is there another reason? I think there's another reason. Claire, she is doing robotics. I think she works in Peter Abeel's lab. Jillian, comp bio. Again, algorithms are everywhere. He likes swimming. Who is this? Henry. Hermish likes running. Ida is from China and Singapore, and she likes Phil's Rosé coffee, which has changed her mind about coffee. Jialan Lee, which I'm sorry for the way I pronounced, is from here, which is above North Korea, and so she probably has a big coat, right? I mean, that's really cold up there, right? Like next to Siberia. Okay, so he's a math major, Jiazeng. Jerry, I know Jerry. He likes this course. Kadar, hiking and basketball. Lynn, she's a grad student in the theory group. Prasad and I are in the theory group. Nate says LaTeX is a problem. It takes a while. I use LaTeX. It's good. Noah likes rock climbing. Rishi, he has a lot written there, but he's tall. He's a tall guy. And Sean, he's also tall. Tarun is a grad student. He comes to my office and asks questions that I have no idea what he's talking about or tells me stuff. He's also in the theory group. Teddy is like South Park. I wasn't sure about this quote. It probably doesn't belong on our webpage because it's from South Park, but okay. Tiffany, cats and hammocks. Varun, I don't know Varun, but he put some slides up for you. Vishnu, he says he's really into theoretical computer science, and he is. I think he's working with Professor Raghavendra. And we have readers who are wonderful people, but they're the ones you'll be interacting with through Gradescopes. So be nice to them, and they'll be nice to you. They'll be instructed to try to give you good feedback on your homework, and also when you have regrades, they will be instructed to try to clarify the issue rather than just say no, or just say yes, right? Really try to get you to understand it. Regrades are an opportunity for you to either get your points back, which we want you to get your points back if we make a mistake, or to help you understand why it was wrong. Okay? Okay, so that was that. Okay, now which one is it? Go Shift P. Damn. Yeah, that's what's going to happen. Okay, that was the staff. We mostly use Piazza, so Piazza is something you should be on a lot, and particularly we have a weekly announcement. That's the one thing we're going to kind of be jerks about. If you don't understand, if you don't read the weekly analysis and ask us questions about stuff in there, that's like a little annoying. So don't, really read the weekly announcements, right? That way you'll know what's happening. Okay. Yeah. So LaTeX okay, scanning's okay. Yeah. Any questions about administration? Okay. Okay. So okay. Does a list have a cycle? This is a puzzle. It's like a coding interview puzzle. You want to give an algorithm or method to figure out whether a list has a cycle. Okay? So now this question is loaded, right? Already it's loaded. Like you're supposed to know what a list is, right? Do you know what a list is? Yeah, a list is something that has some content and a pointer to the next cell, right? It consists of cells, and a list consists of a cell along with a pointer where it has some a value in it, and then a pointer to the next cell, right? That's what a list is. Okay? So now the question, what's the question even mean? The question means you're given one of these cells, okay? And now I say, okay, you have a cell or some entry into the list. You want to tell me whether it has a cycle, okay? So you have to give me an algorithm to do that, okay? Okay, so that's what I mean. You have an access list as a point to some first element. Now, why is first element in quotes? Because if it's a cycle, there's really it's not well defined what the first element is. Does that make sense? Yeah. Okay. So what you do is here's an algorithm. You mark the first node, right? You have a node, you have a cell. You mark it. You say, okay, I'm going to put a mark on this cell. Okay. And then then you go to the next cell, and as long as it's not marked, you keep going, and you keep going until you come back. If you come back, if it's on the cycle, you'll come back and see the marked node, right? Does that make sense? Okay. And the intuition, the claim is either there's no next cell. At some point, you run out of list, and you stop and you say there is no cycle in this list, or it detects a cycle. Okay. Okay, so now the intuition is that if you're on a cycle, you have to return. That's the intuition I said. That was the argument that I sort of made when I devised this scheme, right? So does this work? Does this work? Will it always detect a cycle in the list? Okay, who thinks yes? Okay. Who thinks no? Okay, so the rest of you don't think at all. That'll change by the end of the semester. Sorry. Okay. Having no opinion is probably a reasonable thing in many contexts, but okay, fair enough. Okay, what about this? Now would you change your answer if you said one or the other? Would this algorithm detect this cycle? What do? Like we start at the first node. Here it's clear what the first node is. So you start here, and then what happens? Well, you mark it, and then you go around here, and you just keep going forever. Right? So this is problematic. Okay? So the answer is no. Okay, what's the answer now? No. Okay, good. Everybody raised their hand. No. Okay. So the first node's not in the cycle. That's the problem with intuition, right? The answer is no, right? So, and now the thing is, here I already sort of did some work for you, or somebody did, the Oracle. Somebody gave us this example, right? It was a gift to get this example. And then you're saying, oh no, because of this, right? This is a gift when somebody gives you an example like this, right? Well, what was the problem here, right? We said if the starting node is on the cycle, right? And then that's what even you can see where the problem is even in the intuition. I proved this works in this case. This is an actual valid argument, but it uses this assumption if you're on the cycle, right? And so the problem is the starting point is on the cycle. I was like, well, was the starting point always on the cycle? Then you can sort of think about it. And then you can say, well, maybe it's not on the cycle. And then you think about generating an example. Right? You're not going to get these gifts in real life or when you're on the midterms. Maybe. I will give you some. But in some sense, you'll have to figure out yourself what the example is that breaks the algorithm, as well as the proof. And then you go back and forth. There's this iterative sort of thing where you go back and forth between, here's an idea, does it work? No, it doesn't, etc. Okay? Okay, so here's the way to actually do it for your interview. So here's the step. You just repeatedly do this. You have 2 pointers. You start with 2 pointers, and you have them point somewhere in the list. Okay, maybe at the same place. Okay, you start at the same place. Okay, then what you do is you you advance pointer 1 twice, right? You dereference the cell once, and then you dereference it again, so you're 2 ahead. And you advance pointer 2 once, so that one just goes slower. So the pointers are moving along the list. One is going fast, and one is going slow. And if they're ever at the same place, you report a cycle, right? Because for them to get back to the same place, if you report a cycle, the previous algorithm worked. If you reported a cycle, you definitely came back, right? Here, if they get to the same place, again after the start, then that means there must have been a cycle, right? Because one is always ahead of the other one. How did they get to the same place? Because one must be going around the cycle faster. Okay. Okay. Here's a picture, and let's say at some point there's the red and the blue pointer, and now I'm going to say if there is a cycle that you should report it. Okay. So if there's no cycle, the slow pointer never catches the fast one. This is another form of the argument. This is what I just said about the fast pointer is always ahead, right? If there's no cycle. Okay. Yeah. Somebody say something? Okay. So if there's a cycle, both pointers at some point will enter the cycle. Okay? Like in our last example, if they've started here, they would enter the cycle essentially right away. Okay? So now let's think about a way to set up the argument that the fast pointer sort of catches up to the slow pointer. So at some point it looks like this. They've both entered the cycle. And if there's a cycle, you can't leave the cycle because every cell only has one out pointer. Okay? So once you're on the cycle, you're on the cycle forever. And it looks like something like this. The blue pointer is somewhere, the red pointer is somewhere else. And let's say at the beginning, the distance from the fast point, just going forward from the blue one to the red one is d. Okay? And now after you dereference once, you take one step in the algorithm where you move forward the blue pointer twice, and you move forward the red pointer once, what happens to this distance? What happens to this distance? Yeah, it decreases, right? So what happens is the blue pointer moves forward 2, the red pointer moves forward 1, and the distance between them is now d minus 1. Okay? Does that make sense? So this is a full argument, right? So even for this simple problem, you should really sometimes we do this, right? Prasad and I and everybody who does these kinds of algorithms. We're like, oh, this is how you do it. And then we get worried. Oh, maybe that doesn't work. And then you're like, okay, well, how do I make an argument? And it just goes back and forth. And sometimes it's even the next day, right? You just have to keep plugging away and come up with the cleanest argument you can, right? Yeah. No. They start at the same place. And so, like in a cycle, the way I'm defining the direction is wherever they are, I start at the blue pointer and go forward to the red pointer to define my D, right? Yeah, good question, right? So he's saying here, I set it up so the red pointer is ahead of the blue pointer. But in fact, on a cycle, you could always go forward from the blue pointer and get to the red pointer, okay? And you're just counting the number of steps. Yeah. Oh, you're supposed to, I'm sorry, I should have added one with, you're only supposed to use 1 unit of space, or constant amounts of space. So the question itself has that coded in. Okay, yeah, he's asking why can't you just mark everywhere? It's like you make a big mess when you mark everywhere. So you can only mark a few places. That's the question. Okay? Okay, so good. Okay, so that's the runtime. And then the second thing in our 3-part problem is we also analyze the runtime. And this is n steps to the cycle. If it's a list, it takes sort of n steps to traverse it, no matter what you do. So it's order n time. Okay? And the additional storage. The key here, which I should have said at the beginning, is that there's an additional storage cost of 2 pointers. Yeah. Yeah, I'm assuming that the way the list is represented is you have a cell and you can chase the next pointer. That's all you can do. Okay? So if you have a list, you have the car and the coulter. You do scheme anymore in 61A, huh? Yeah, but it should all be in scheme. I don't know why they did this with Python. What the heck? But anyway, John De Niro is good enough to overcome the burden of Python. But the coulter tells you the next element of the list, or the next, okay? And you reference it that way. Yeah. Well, we don't have infinite lists in computer science. Yeah. Yeah, we just don't. Okay. Okay, so that's it. So what are these puzzles? They're solutions to these puzzles. And in some sense, they're algorithms, right? For computer science, they're algorithms. These puzzles are very rarely just like a little puzzle that's 9 by 9. It's some big object that scales and gets bigger, and like maps that get bigger. And you're solving problems on them, which are puzzles. What's the shortest way from here to Stanford? You never want to go to Stanford, so who cares? But I don't know. Some people have reasons to be there, I guess, which are correct. So you have to argue they're correct. And these correctness arguments are they're arguments, right? We're making proofs, but they're arguments. And in this class, we want them to be efficient. Okay, that's what the point of this class is. You want your algorithm to be efficient. Okay. Okay, is it useful? Yeah, it's useful all over, right? There's this whole thing called the Human Genome Project, where they took somebody's DNA or a few people's DNA, and they started reading the first character, then reading the second character, then reading the third character, using chemistry, like test tubes, and they did this stuff, and it's an A. Oh, it's a C. Well, it's 3 billion long, so it takes a long time, right? So that's not what they did. What they did instead, it takes very long, it's error-prone, you're doing chemistry. What they did is they cut it up into a million pieces, little bitty pieces, okay? And that you look like this. And then you could read in parallel. You could do all this chemistry in parallel now with these little pieces, okay? Because chemistry, there's a big soup, you can make a lot of them, you don't have to do it sequentially. And then what they did is they tried to assemble these into a consistent string. So what they would say is these all have to overlap because we're cutting them randomly. So there's lots and lots of overlap, and now you can see that once you do that, you can put this string back together to be that string. Okay? And now really this is oversimplifying because you actually have hundreds of these at each place, sort of shifted by a bit. And this is how they reassemble these things. So this is how you do 23andMe and various other things work this way as well. Okay. Another thing was what is good on the web? What do you do now? What do you do when you want to find something on the web? Yeah, you search. Okay, back in the old days, like we had stone tablets and we didn't have Google. Okay, so what we had is we had this capitalistic model. You've heard of capitalism, right? Yeah. And so what we did is whoever paid the most would get their things listed in the search engine. Literally, the first GoTo.com, they got a patent for this. Okay, and so these guys, Brin and Page, Larry Brin and Sergey Page, or the other way around. That was a joke. Follow link, follow link. They're like, let's see what people do. Back then, what you did, the way you used the web, is you looked at it, and people would put my favorite links, and you'd go click around, right? And so they had this model. This is what people are doing on the web. They wanted to give people what they wanted. They didn't want to just make people pay. Now they make people pay. But okay, back then they were trying to give people what they wanted. Okay, and they still do. So this is what they noticed that people would do. They'd follow a link, they click there, they click there, they click there, and then eventually jump to a random place. Okay? So popular pages are sort of desirable pages in this model of how people behave. Okay? So their page rank was they would do an algorithm on this graph and say, if you follow this random surfer model around this link graph, where would you end up most often? And that's what PageRank does. So it's a popularity for a random surfer. They're trying to give the people what they want. Okay? So then they would, when you got your search results, they would see all the pages that had something to do with what you said, and they would rank them in the order of popularity by giving the people what they wanted. Okay? So, it made us happier, a lot happier. It's much better. It is what Google does. There's also issues. So since then, there's wars between the people who want to make their web pages big. That what they would do is make their web pages all point to each other. So then you get trapped in their little cluster, and various things happen. But now we have a different model, right? This algorithm was so popular that Google is so powerful. Now we have a different model of the user. Is that you just Google or search. I guess there's other ways to search, but okay, and so it's everywhere, right? Everywhere. I even used it. I worked at this company. I used to introduce myself as having worked at a company, but I punted that. So it's everywhere. Akamai does content delivery on the web. You can understand in the internet there's all kinds of algorithms, so that's one of them. Okay, so that's sort of just an introduction to algorithms and what you're going to sort of get out of this course, right? You'll get access to these powerful tools that are used everywhere, and you'll be able to use them responsibly, hopefully. Okay, so what is that? That's one. So this is how people calculated before. And they had algorithms, right? Algorithms have been around, methods to compute things, right? So they had this thing called the Roman numerals, which is that's 1, that's 5, 10, 100, 500, 1,000. So now, once you have these basic units, you can write other numbers, right? V111 is 8, right? Because that's 5 plus 3, right? That's D is 500, so that's 500 plus 100 plus 50. Yeah, L is 50. I didn't include it. 10, 10, 1. Okay? I don't know. That's something, This is, I can't, it's incomprehensible that these people actually use this system, but this is a system that apparently was around for quite some time. Now, can you add them? Can you add these numbers? I mean, one could. Yeah. What did I do? I can't add them. Okay, this is beyond my capability. But I can translate them to something else, which are the numbers that we use today, and say, okay, that's 1448 plus 671. Oh, look, that's this year. This is telling us, this formula is telling us, obviously, that it's 671 years since the Gutenberg printing press. And this is an amazing invention, right? It gave reading and writing to everybody. I mean, at least it started to, right? This is a big transition for humankind, right? And so, Okay, so now, the concept, now they could do it. They were Romans, right? They conquered like all of Europe and stuff. So they would go ahead and figure out how to add these. They weren't so lazy. But can you imagine multiplying those? That's problematic, right? Okay, from India, there's this guy, Al-Khwarizmi, who's a Persian. He went to India. And what he did is he imported recipes for adding and multiplying, solving quadratics, all these algorithms that they had developed in India. And these are algorithms, and in fact, his name is the genesis of the word algorithm. But it's not like the Indians were the only ones who had better systems than the Roman system, right? The Mayans had base 20 because I think they wore sandals probably in Central America. So, you can do base 20. We do base 10, right, because it's cold in Europe or something. So there's dots and underlines. So this would be 13. They would do 5s and 3s. The Babylonians use base 60. It's not... These things, people are the same. We all are really in a mad pursuit for efficient algorithms. So together, all cultures, right? So we have all these things. India, my mom used to tell me when I was growing up, it's like, because I'm American, my mom is from India. I was born there, but I don't remember it. And she said, India, they invented zero. Now, as a kid, I was like, I don't know that that's such a great thing to invent. You invented nothing. I'm not so sure that's good, right? But, okay. But what she meant is it was good. She meant there was a place value system. And they invented the zero to take the place there of 0, to move you over and multiply by 10. Right? And decimal system. Okay, so we use base 2, obviously, in a computer. These are the representation for modern computers and communication. Those of you who took 70, we talked about the hypercube. Properties of the hypercube is 0-1 strings. It's just how do 0-1 strings behave in this world? How do algorithms or functions on 0-1 strings behave? And this is stuff that we really study in computer science. Prasad is one of the ones who actually understands these things better than almost any human. These things are still fascinating objects. Okay, so so he brought it back. He did all this stuff, right? He's a mathematician and astronomer. He was cheating because he actually had efficient ways to do everything. But Fibonacci is the one who popularized this use. He traveled to Persia, or I guess it propagated through the Middle East, and he traveled there and he brought it back to Europe. Okay, so we're going to go back to Fibonacci numbers, right? You've seen these before. We're going to talk a little bit about them in the context of efficiency with computing with numbers. Okay, so this is the definition of this sequence, right? I guess it's the number of rabbits you get. You get 2 rabbits, they breed, you get more, and so on, right? So you add the number of rabbits you had the previous day, plus the number of rabbits you had the 2 days previous. Okay? Okay, and you've done, who remembers, did you guys do this in 61A? Yeah, okay, everybody did this. This is how you write a recursive program that does this. It's just implementing the recursive function. Is this correct? It's correct because it's just implementing the recursive formula, right? It's almost by inspection. Okay? So, right, it says here, if it's small, that's the base case, 0 or 1. If it's larger than 1, then you assume recursively you're correct here, and you're correct here, and you add the numbers. Okay. So the runtime, what's the runtime? Yeah. O of n squared. Okay, so, yeah. it's more than that, but it's a little hard to see. And so, and in fact, I'm not going to tell you all the reason, but I'm going to tell you it's way worse than that. Okay, and it's in some sense, you could write a recurrence for the runtime, and the recurrence looks very much like the actual Fibonacci thing, right? I say, well, I make a recursive call on this on n-1, I make a recursive call on n-2, and I add some constant, like 2, because there's 2 instructions in this code. Okay, so oh my God. Okay, so a t of n. Now, so basically, this tells you whatever the running time of this is, it's at least as big as the actual value of the Fibonacci number. Okay, so I'm going to tell you this is a very bad algorithm. Okay, so there's f of n-1 plus f of n-2. If you unfold it and you look at this, let's see how fast this thing is growing. I'm going to try to play with it a little bit and tell you it's going to just blow up. So, again, the time is going to be as big as the Fibonacci number. And the next step is say, how big does the Fibonacci number get? Okay? I'm just arguing it's bad. Okay? So what I do is I unfold it a little bit. And what do I see here? Let's ignore this term. Okay? Just ignore this term. I see that f of n is at least as big as 2 times f of n minus 2. Right? So, by induction, we see that f of n is bigger than 2 to the n over 2. So this algorithm takes more than 2 to the n over 2 time. So it's really exponential. It's not n squared. Okay? And from the book, it's actually worse than 2 to the n over 2. I just did a quick proof here that says this is bad, but you can actually see just how bad, in some sense, if you go look at the book. Okay? So for n equals 100, this is around 2 to the 64 operations, which is more than 1,000 years or so on a fast computer. So this algorithm, I think technically you would say it sucks, right? It's terrible, right? It's a nice illustration of recursion, but it's a terrible algorithm. Okay. Can we do better? And you did better in 61A, right? What was the other fib you wrote? The iterative version, right? Okay, so here, I don't know why I wrote it in this bizarre way, but this just writes out the Fibonacci sequence in an array. Okay? But here, there's no recursive call. It's quite easy to analyze. What you do is you just count the number of times you go through this instruction, which I'm going to assume is fast. Okay, so order n operations. But it's not quite n operations, because one problem is, let's see what it does. Okay, let's see. This is fib. Okay, that's the recursive version. I wrote it slightly different, the iterative version, and I'm timing it for various things. Okay, so the recursive version, I go from 1 to 20. You could see that from 20 to 21, it goes up by a factor of 2 to the 0.64, roughly. That's the 2 to the 0.64 times n. When you change n by 1, you multiply the time by 2 to the 0.64. Whereas here, when you double the size here, it should double. Okay? If the time is order n, to go from 64,000 to 128,000, it should double. But it's going up by a factor of 4, roughly. Okay? And this one is also going up by a factor of 4. When I double the size, if it was actually linear, if the size was twice as big, it would be twice as much work, right? But in fact, it's going up by a factor of 4. Okay, why is that? Okay, Control Shift P. Okay, so we see there's an issue here, but when we try it, and the question is because Fibonacci, these numbers become big, right? This is all about the same issue that the Romans were having and the Indian, Arab, Babylonians solved, right? is that the representation of this number, if you did it in Roman numerals, it would also be big. But the representation in bits is only 0.64 n bits for the nth bit. But 0.64 n bits is still, you still have to worry about the size of the number itself. And you have to account for that. So how many bits are in f of n? It's log base 2 of f of n, which is this many bits. That's the representation in binary. How long does it take to do this addition? Well, you add two numbers, and you get order n time, right? So now how long does fib take? It's n additions, and most of the numbers are around order n size. So there's at most n squared. Okay? Okay, so for fib, this is something you see, right? So it has a much nicer than the exponential one, right? We can only compute out to 20. Whereas I was computing hundreds of thousands for fib, iterative fib, right? 20 is a disaster. If I did 40, we wouldn't finish, okay? But see n squared time, if you double the size of this thing, if you double the size of the input, you get 4 times the runtime. Okay, and that's what I was getting, the factor of 4. It sort of told me I was going to get n squared as the running time. Okay, so scaling the input by c. If in general we care about polynomial time algorithms. We don't want the size of the problem n to be in the exponent. We want it to be the base, and we want the exponent to be some constant. N squared, n cubed, 1 would be linear. Okay, so scaling the input by c grows the running time by c to the k. Okay? Does that make sense? Right? This is exactly what happened here. If it's an unfortunate use of the c, but if I change this thing to a 4, you would get a 16 here. If I change this to a 5, you get a 5 squared here. Okay? So if you change the size of the constant by scaling it by constant, you get another constant. Okay? So whereas it scales the runtime by a constant. It's not true for exponential algorithms. If you double the size of the input for an exponential algorithm, it squares the runtime. So if something took 1,000 seconds, it's going to take 1,000,000 seconds if you just grow it if you double the size. And then after that, if you double the size again, it'll be 1,000,000 times 1,000,000, rather than scaling by a constant. So exponential time algorithms are a disaster. Okay, and now we use this O of n. You've seen it before in 61b, because I didn't really care about whether it was n minus 2. The number of additions for Fibonacci was a little less than n if you didn't have to add the first two. But who cares? You sort of discussed this both in 61a and 61b. And you can see that the recursive fib has a faster inner loop than the iterative one. But it doesn't matter, right? Because we care about things as they get large, as people really use them. Okay, so this is the difference between these two algorithms, and this one is a disaster, this one's fine. I could run it to thousands, hundreds of thousands. Okay? Okay, so that's what we saw. If squaring the runtime, it matters the units here with the milliseconds, so you didn't quite see a square. What I did instead is just added 1, and you'd see the doubling. Okay? Okay, so this is what you learned in 61C, 61B, but we're going to do it a bit more formally in this class. Okay? So 2 to the n squared asymptotically, we're going to care about asymptotics mostly, unless we specifically say otherwise, which we will do only rarely, and not for runtimes. 2n squared is asymptotically the same as 4n squared. We just think of those as the same growth functions. Okay? Both are O of n squared. And 4 log n is asymptotically the same as 100 log n. We just think of that as O of log n. We ignore small order terms like 2n squared plus 100. We think of that as O of n squared. Again, n squared grows faster than log n. So we think of that as O of n squared again. So the 100 here is a small order term, and the 100 log n is a small order term. And this is an upper bound. N squared is also O of n cubed. A function here, big O, is an upper bound. So when you say this n squared is not only O of n squared, it's also O of n cubed. This is This is saying that this function grows, in some sense, asymptotically at least as fast as this one. So this grows faster. Okay, so formally you can you have this. This is a more formal statement. Is g of n is O of f of n. It's a function which has sort of is smaller than this function in terms of growth as n goes to infinity, meaning that there's some constant g of n, c, that you multiply f of n by to get it bigger than g of n. Okay, so that's the way the book defines it. There's a variety of ways to define it. You could define it as a ratio and a limit as well. Okay, and now you can do the same thing for a lower bound. And a lower bound is here, right? It's the same thing. You're saying it's omega. 2 of n squared is omega of n squared. And now it's also omega of n. It takes at least as it grows as you go to infinity, it grows at least as fast as n. Okay, so you can do it this way too. Okay, so now there's two things, and I'm going to leave you, I guess, with the puzzle because that's all I have time for. But it's an interesting puzzle. Okay? So and it's an interesting puzzle that you can just read the book, and I would encourage you to do that even before lecture. I think many iterations are good. It's fine. Okay, how long does it take to add two n-bit numbers? So we've seen this, right? This is how you add it. You put them in columns, you carry, blah, 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 right? It's O of n. So can we do better than this, you think, to add two numbers? Can you do better than O of n? Well, the output is O of n. If you have two n-bit numbers, the output is n bits. So even to write down the output takes order n time. Okay, so you probably can't do better than this, right? I mean, unless you use some other, you can't do better than this. So this is sort of optimal in a sense, right? If you want to write out the whole number, it takes order n time. Okay? Now, so multiplication. Now, remember how to do multiplication? Well, you multiply 1 by everything there, and you put that there. You multiply 9 by everything there, right? And do all the carries. And you keep doing this. Now, if it's n bits, you took each one of these numbers in the bottom one, and you multiply by every one of the numbers in the top one, every one of the digits. And then you added them up. So this is, each one of these numbers is n wide, and it's n tall. So the total amount of work you're going to take is O of n squared. Okay? Okay, so is this the best possible? Do you think we can do better? Like here, writing down the output is only 2n. The number of bits in the output is 2 times n. How about here? So you could conceivably have a more clever algorithm. But every digit in x sort of must multiply every digit in y, right? Otherwise, how do you get the answer? Right? So I'm trying to prove you can't do better. Right? So that's theta of n squared, right? There's n choose 2, right? Or n times n. Okay? Is this the best possible? Can we do better? What do you think? Who thinks yes? Yeah, well, you read the book, or maybe. I think no. Okay, I really cannot believe you can do better. It defies me. But we can do better, and I don't believe it. But I'll show you how. Okay? Really? I mean, this is really shocking to me, right? Really? You could do better? Okay? So this is chapter 2. But let me show you. Let me show you that, in fact, not only can you do better, you do better. Okay? And then I'll let you go. Okay, it's going to take you to concentrate. You got to concentrate. So... Okay, so let's look at this. Okay, so what we're doing here, okay, let's look at it real quick. Okay, so what we're doing here is we're multiplying 1,000 bits, something with around 1,000 bits, or a little bit more than 1,000 bits by around a little bit more than 1,000 bits. 3 to the 1,000 times 7 to the 1,000, some arbitrary, bizarre, big number. And then I did the same thing, only I multiplied two numbers, both of whose representations are twice as big. Okay, this is like a little bit, it's picky, it's bit hacking a little bit. You need to see how big these numbers are, not in value, but how many bits. So this exponent here is telling you how many in some sense, the scaling behavior of the number of bits. So the 1,000 there goes to, the 10,000 goes to 20,000, goes to 40,000, and roughly you see that the standard multiply is going up roughly by a factor of 4, right? You see this? Okay. So this is just using standard multiplication like you did in grade school. And it goes up by a factor of 4. Remember, when you double, it should go up by 2 squared, which is a factor of 4 if the algorithm is n squared. Okay? It goes from 2 to 2. If you double, it goes from 2 squared if it's n squared. So this is an n squared algorithm, roughly. There's some constant factors that are confusing things, but... And now, what does Python do? This is a demo of Python multiply. Literally, this is what is coded into Python. Does it do better than grade school? Here's Python multiply. It's multiplying. It's doing Python multiply, right? X star y. Okay? Instead of the algorithm from grade school. And now, as you go up, look, it's going up by less than a factor of 2, 4. Right? The time here is going up by a factor of 3. Right? Or 2.68. It's a little less than a factor of 3. Okay? And so on, and so on, and so on. Okay? So that is telling you the world is different than what you knew in grade school about multiplication. Okay? And that's something we'll start with. But okay, let me take home a few, let me just tell you a little bit about what I want you to remember. Okay, so one thing to remember is that, okay, what I really want you got to think of size. Here, for these number algorithms, there's 2 sizes that are happening. The values of the number and the size it takes to represent it. Okay? And so when we want things to be efficient, we want them to be efficient in the size of things to represent it. Okay? Otherwise, we're back to Roman times and may have to return to feudalism and bad stuff. Okay? So think about it this way. Okay?